In class today, we had an opportunity to begin studying the second half of this course, which focuses on the topic of vectors. And we didn't have a chance to finish the introductory lesson, so I wanted to present a few slides of information for you, and then tomorrow we can spend some time in class focusing on more problem-based work. So we left off here at the Pythagorean Theorem, and it is used quite often when we are trying to determine the magnitude of a vector. So let's just fade this in. What you do need to take note of are the representations for the vector. In this case, vector v, its magnitude could be denoted as such with the absolute value bars. We also have this notation where we have the double set of absolute value bars, or in some cases you might just plainly have the letter denoting the vector, in this case just a v. Typically what I will do in this course is to represent magnitude. I will adopt this notation and will sometimes work with this notation here. Predominantly this one, as it specifically relates to an earlier part of the course where we were dealing with the absolute value of functions. So in example 4, what I'm going to have you do is I'll model 1, and I'd like for you to follow through on the remaining 2, and that is to say, pause the video, give yourself some time to think, and then calculate. So we're interested in the magnitude of the position vector, OA. And of course I say position vector because it's referenced at the origin, or to the origin is where we have the tail, and then the head of the vector is at point A. So as far as its magnitude is concerned, if we consider a right-angled triangle, which we'll create here, you can apply the Pythagorean relationship to solving for the length of line segment OA, and in terms of the directed line segment vector OA, we would have the following relationship. Okay, so we would take the square of 2 and add to that the square of 2. At the end of the day, if you simplify, we'd have 2 root 2. So again, take a moment to process the magnitude of AB and BC, and then check your work. Okay, so trusting that you did pause and attempt the work, you'll notice that the magnitude of vector AB, okay, that is this particular vector here. So tail at A and the head at B. Okay, you would have to use the Pythagorean relationship in order to determine its length. So you can therefore see that we have a vertical component of 3 units here and a horizontal component of 1. Hence the reason for the values you see here. We have vector BC. Okay, so not a position vector, but rather another vector, a displacement vector. So BC, our diagram getting a bit cluttered, but it starts here, its tail, and then the head over here at C. Okay, using the Pythagorean relationship, you can see that by the right angle triangle, we would have 4 units as the horizontal component, 2 for the vertical, and then a final answer of 2 root 5. All right, let's move forward. Vector mathematics applies to higher dimensions, so certainly 3 dimensions, x, y, and z. So we have here on the left-hand side a cube. It is also known as a cuboid or a rectangular. Here's a tough one here, a parallelepiped. So try to say that one 10 times fast. So the following relationship is true or a parallelepiped, if you want to consider the diagonal or these cross diagonal AG, so from vertex A over to G. So if you can envision looking into the cube and following the diagonal from A to G, the idea there is to come up with the length of that particular expression. So when you see the letter D, I know you see vertex D, but big D and lowercase d don't have a correspondence here. The letter D in this case seems most suitable to represent a diagonal of the cuboid. Okay, so in order to determine that, we take the values of A, B, and C and apply what is much like a Pythagorean relationship. Okay, if you were to consider this any other way, what you might want to think about is the following. That in order to get the length of the diagonal, if you were to determine the length from A to C, and to that, consider the right angle here, and then from C to G, you would have that particular length, or be able to calculate the length for AG. You can do a little more background work on this to try to make connections as to why you simply take the three lengths or the three dimensions, but more or less that is in a nutshell. If you were to use the lengths of A, and let's just call this one B as its opposite B, same length, you can call it B prime if you want. If you were to combine those two measures in the Pythagorean theorem, you would come up with a measurement for this directed line segment here. Okay, I'm just going to put a check mark on it so you know the one I'm talking about. It would then follow through on the use of side C along with the answer for our check marked side that would give you the length of AG. Okay, so take a moment and reflect upon that. You can see how A, B, and C are now being used to calculate the length of the diagonal. So with that in mind, what I would have you do is to follow through on determining the magnitudes of vectors AB, BD, as well as BH. So please take a moment to pause the video, attempt all three, unpause, and check your work. Well, now that you've given it a try, do take note that the magnitude of AB is simply the side length that has been provided. And that side length here is 10 centimeters. So hence the reason for the 10 centimeter measurement we have here. And that's a very poor color to be demonstrating online. So let's just get rid of those. Let's choose something more appropriate. This will work. That's a little bit better. Okay. For BD, you can see that you would have to use two side lengths. Okay, so we do need to use 10 and 10 in order to calculate in that right angle triangle the magnitude of vector BD. And last but not least, if you were to use the Pythagorean theorem in 3D, that is according to this relationship right here, you're going to end up with the following. Okay, so that turns out to be the root of 300, and as a mixed radical, you would have 3 root 100. Oops, sorry, not 3 root 100, but root 100 multiplied by the root of 3, which we know to be 10 root 3 centimeters. So in thinking about pausing, unpausing, and trying to understand the material, sometimes a common question is, the video was fine, but I didn't have anybody to interact with, be it peers or my teacher. So what I would impress upon you is to take time out to perhaps message and or call a peer to discuss what was shown in a video, or watch a video together, online at the same time. Another option too is to practice a particular form of note taking, which is classic to a number of classrooms, university classrooms. You might be coached into preparing your notes and then writing down questions, be them in the margin, on sticky notes, about things you'd like to ask or know more about. And then as a last step, summarizing. So going back over what you've written and trying to determine what it is that you understand from the lesson. So such a powerful method, especially when we are flipping our lessons like this, watching at home and doing the work in the classroom. It's really key that you come in with pointed, that is specific questions regarding what you're studying. So let's finish this up here. We did cover item H and I, maybe even J. Let's have a look here. We'll do another few minutes on this. We have a regular hexagon, A, B, C, D, E, F, with side lengths that are equal to 2 centimeters. So of course, regular meaning all side lengths are equal. I'd like the magnitude of the following vectors. So we're looking for AB. We are also looking for AC. And we're going to pause the video just so I can take a call. And you also need to determine the magnitude of vector AD. Okay, so I think it's very straightforward. AB, quite obviously, is simply the length of side AB. So we have 2 meters is the magnitude. But what you're going to have to consider now is perhaps some additional mathematics that would be required to determine the length of AC. What I do want to impress upon you is the fact that you do have a triangle. Okay, specifically you have a number of them, but if you look at vector AC, it happens to be a side in triangle ABC. So really what's going to happen there is we're going to have to entertain some other form of mathematics. Okay, and specifically, if you want to consider this hexagon, that is a regular hexagon, has 720 degrees, given that there are 6 angles in front of us here. Let's see, what do we have here? 1, 2, 3. We can gauge that any particular angle is 120 degrees. So for instance, angle B is 120 degrees. Okay, that also means that we have the ability to determine the size of angles. I don't want to say A and C, but specifically BAC, which is this one here. And then of course you're able to determine the measure of BCA, which is the angle that's up here. I'll just give you a little more additional information here. Let's consider the calculation on AC. Okay, and we have 2 multiplied by 2 sine 60, okay, giving us 2 root 3 meters. So we'll look at the reasoning behind that. I'll have you pause the video and then attempt to calculate AD. You can unpause and check the remainder. Okay, so if we continue considering the work that has been done for part B, let's just add some clarity to the diagram here. So we're going to clear this out for now. And let's just trace out exactly what it is that we need to do. So we have sides A, B, and AC, and we're after the magnitude of vector AC. So with that in mind, do realize that angle B is equal to 120 degrees. Okay. Using the information that we have in hand, we have side lengths of 2 and 2. Now we could very well apply the cosine law to this particular scenario and or the sine law. So what I'm going to do is move forward, and I think I'm going to relate the sine law to you. Being that we have 120 degrees already accounted for, we can see that angles A and C are equal in measure, and they're both 30 degrees. So I just want to make clear why the answer key is as such. Okay, the approach will be a little bit different, and I recommend that you follow suit with whatever skills that you have regarding finding side lengths. So in this one, we can set up our sine law expression, which is going to relate the side length in question, and we're going to compare that to the sine of 120. That is going to be in ratio or equal to another ratio, which is going to be 2 being compared to the sine of 30 degrees. When all is said and done, what we do need to realize is that the question mark, or the length of that side, is going to be 2 sine 120 all over sine 30. What it comes down to in terms of the expression given is that sine 60, here we have a quadrant 1 angle. And what we do know is that the quadrant 1 angle, 60, and the quadrant 2 angle of 120 do produce the same sine value. Okay, so this representation uses the quadrant 1 angle. If we move further on this, we know sine 30 is 0.5. That's equivalent to, we could have stuck with 120, would not have made any difference whatsoever. And when you divide by 0.5, okay, when you divide by 0.5, you're really going to end up multiplying by 2. So hence the reason why we have the extra 2 in our answer key. Okay, and if you find the exact value of sine 60, you'll recognize that it is root 3 over 2 using your unit circle. So we'll end up with 2 multiplied by 2 root 3 over 2. You can see how one of these 2's is going to cancel, and we're left with 2 root 3 meters as the magnitude of vector AC. So this video is actually progressing in terms of its length. We're going to stop it here, and we'll continue these examples tomorrow in class, followed by an assessment quiz to see how well you've understood the concepts.